Hello, everyone. Welcome back to CP 517-WS. This is Digital and Computer System Architecture, Part 3, Static and Dynamic Branch Predictor. Static branch predictor is how we do either what was taken or what was not taken, right? So we should scheduling code around delayed branches. We can reorder code around branches to introduce delayed slots, and then we can predict branches statically taken during compilation. The simplest scheme is to predict the branches taken. Average misprediction equals untaken branch frequency, that is 34% in the stack at a branch. More accurate scheme predicts branches use the profiling information, like the history of the earlier ones, to predict. As we can see here, for the static case, the miss rate is ranges from 4%, 22%. This is really high. Okay. So dynamic branch prediction. Why do we introduce dynamic branch prediction? Because the underlying algorithm has the regularities, right? For example, in for loop, if we're most likely gonna be the first iteration, second iteration, maybe a couple of iterations gonna be taken, right? The first is taken, second most likely gonna be taken, except, excuse me, the last exit entry, right? And data that is being operated also has regularities. Instruction sequences has redundancies that are artifacts of the way that human compilers think about problems, right? So for some problems, we repeat to similar things. Is dynamic branch prediction better than static branch predictions? It's typically like that. Well, there are a small number of important branches in programs which have static behaviors, but not always, right? So some branches might take better benefits from static, but dynamic branch prediction wouldn't do very poor. It's probably slightly worse, but typically dynamic branch prediction is better than static one. Let's use this code snippet as an example. For I equals to 0, I less than 10, for this problem, in a loop, if we have one bit history table, branch prediction table, it will cause two mispredictions. So what are they? So the first is the end of a loop, right? When you have taken, you keep going taken until the last iteration, you take taken again, but after that iteration should be not taken, right? This is a misprediction. Well, for the first time, we continue to loop when it predicts exit instead of looping. The reason is also because probably the history of the prior loops, right? To solve that problem, we introduced 2-bit branch prediction. Actually, this is a very, very powerful one. Actually, even today, in a lot of computers, they still use this kind of 2-bit branch prediction. Even we're going to introduce more complicated ones later. So what is the 2-bit branch predictor? It shows here in the slide. We have in total 4 states. That is strong taken, right? Strong taken, weak taken, strong not taken, weak not taken. As you can see here, so the first bit, the most significant bit, is the prediction. It's either taken or not taken, right? The second bit shows what was the prior history. If your prior history is taken, so it's taken and strong taken. If your prior history is not taken, so it's not taken. if your prior history is not taken, so it's not taken. If your prior history is taken from here to here, so it's taken, right? So that's how we understand this dynamic branch predictor. So the first bit predicts it's whether taken or not taken. The second bit shows the history of the prior state, the prior one-step state. So taken together, we can say it's a 2-bit branch predictor. Well, starting from strong taken, it takes 2 non-takens to go to strong not taken. So basically, two continuous not taken goes to strong not taken. 2 continuous taken goes to strong taken. For instance, if we start from this state diagram, here, if we're here, okay. Then what we do is we predict it's taken, then we stay in the strong taken. If it is not taken, so we go to weak taken. If it still is not taken, we go to strong not taken. In a weak taken, if it goes to taken, then we go to strong taken. And then once we enter this strong not taken, if it's still not taken, so we stay in strong not taken here. If it is taken, then we go to weak not taken. Okay. In weak not taken, we can either go to strong taken, because if you are in weak not taken, it must be that your prior step is taken, because that's the only way you enter this weak not taken, right? So you can say this one and this one are relatively intermediate state. Well, in weak not taken, if it's not taken again, you go back to strong not taken. Okay. Well, 2-bit predictor is actually very useful, right? So you can use the history to track what is taken or not taken. But there are cases that 2-bit predictor, like I'm only concerned about my own branch, could be problematic. For instance, okay, we could say you have this A equals to 2, B equals to 2, so you set A equals to 0, B equals to 0, and then it's clearly A will be equal to. So if both of them are taken, this should be not taken, right? So we see this kind of things as correlated branches. Or we say we can consider the recent behavior of other branches rather than just the branch we're trying to predict. This could potentially help us improve the prediction accuracy. A predictor that uses the behavior only a single branch to predict the outcome of the branch can never capture this case, right? So you don't know, because it's really correlated of A and B of the prior branches. So you don't know how, based upon your own case, because A and B could change, right? The value of AA is 2, BB is 2, and later A becomes 3, BB becomes 5, something like this. So your own history previously predicted as taken and later predict as not taken. You cannot use your own history to predict your future. Instead, you can use whatever was happening before the other branches to predict your future. Right? That's how we mean by correlated branch prediction. So you can think you have a history here, right? This history helps you to make decisions. Sorry, it's a history of other branches, okay? It's very important. Other branches. History. So it's not your own history. Okay. So correlated branch predictor is typically called the MM predictor. So MN predictor, does it mean? So we record M most recently executed branches as taken or not taken, and use that pattern to select the proper M bit branch prediction history table, right? So assuming that, then we have in total 2 to M branch history tables, right? Well, since different branches might use different MN predictors, this predictor table will experience replacement. Computers then often have more than 2 to M entries. So that is the number of prediction entries selected by branch addresses. It's like the cache, right? So we cannot just have a single like 2 to M branch history. We might have multiple of them so that we can afford replacement, right? So then taking them together, we have 2 to M branch history tables, multiply the number of branch entries that is a selected branch history, right? And then multiply M bits, because every entry is M bits. Okay, can we use 15 minutes to solve this problem? How many bits are in the 02 branch history, branch predictor with 2K entries? How many entries are in the 22 predictor with the same number of bits as this one? Please pause the video using 15 minutes to solve this problem. Okay, welcome back to the exercise answer. How many bits are in the 02 branch predictor? It's 2 to 0 multiplied 2 to multiply 4K, so it's in total 8K bits. So for these 8K bits, how many entries are there? We can see here. So it's 2 to 2 multiply the number of entries selected per branch equals to 8K. So we only have the number of bits selected by address equals 1K. Right. Here is the accuracy of different schemes. You can see here for 4096 entries, 2-bit branch history versus this the same, right? 2 to 2 of 1024 entries. So it's the same of 4096 entries. We see this one's typically better, right? Because it can better afford, it can better correlate the branch history, right? Because it has the 2 history of the prior branches. And it's actually even better than unlimited entries, like which does not consider the history of the prior correlated branches, right? See here, except this one. And then, right, it's clear. Okay, after we talk about correlated branch predictor, then we go to another predictor called tournament predictor. Tournament predictor considers to split the global branch history and the branch address, right? We mentioned here. We combine the most recent executed branches and the branches addresses selected by branch address. So right now we split them. And then we have global predictor and local predictor. And then we use the selector to choose whether we should go to local predictor or global predictor. Because sometimes we prefer global predictor, sometimes we prefer local predictor, right? So if we can have a better selector, for instance, what current case do is they use the taken, not taken, the 2-bit case. If you guys remember here. Use this one, dynamic 2-bit branch predictor as the counting predictor. So if the global predictor misses 2 shots, then we go to local predictor. In the local predictor, if it misses 2 shots, we go back to global predictor. This is what we call the multi-level branch predictor in tournament predictor design. And as expected, typically tournament predictor has a much better branch prediction, means the way is better, right? This is better. So local predictor is worse than correlated, and correlated is worse than tournament because it combines the both. Okay, the second problem is about branch target buffers. So branch target buffers actually buffers the potential target of the branch, right? So when we predict it's not taken what it's taken, where should we go, right? Where should we go and fetch the PC? When match is found, it's like this, right? So we typically have a PC of instructions, and then we use this PC to look up into the lookup table, and then we predict the next PC. So if this is taken, yes, then we use the predicted one, right? If it's not taken, then that means we can continue to next iteration, next instruction. So the PC is also given, right? That's how it works. Coming to the summary of the dynamic branch prediction summary. So the prediction becomes very important. We're going to talk about a speculative execution where branch is the major problem. Branch history table has 2 bits for loop accuracy, a correlation, like a correlation based using prior history, right? Tournament predictor takes insights to next level by using multi predictors. And branch target buffer includes the branch address to prediction. All right, I think that's it for this part.